What is the oldest light in the universe? It's a simple question, but honestly, the answer is wonderfully complex. You might think of the light from the most distant stars or galaxies. Maybe you've heard of the cosmic microwave background, the famous afterglow of the Big Bang. This incredible signal is often called the universe's baby picture. For a long time, we thought it was the oldest thing we could ever hope to see. It's this faint, ancient light that fills all of space. But what if I told you there's something even older, a light that began its journey long before the first atoms were even born? And this isn't light in the way we normally think of it. It's not made of photons, the particles that our eyes can see or our telescopes can detect. This light is made of something far more elusive, a ghostly particle called the neutrino. These tiny, nearly massless particles are all around us, streaming through the earth, through our bodies, and through everything we know. This is the cosmic neutrino background, the true oldest light. Imagine trying to see something that is almost completely invisible. To understand the cosmic neutrino background, it helps to start with its more famous cousin. Let's talk about the cosmic microwave background, or CMB. Think of the early universe as a thick, hot, glowing fog. It was so hot and dense that light particles, photons, were constantly bouncing off charged particles. They couldn't travel freely. The universe was completely opaque. You couldn't see through it any more than you can see through a thick wall of smoke. This went on for about 380,000 years after the Big Bang, which honestly is a long time for us, but just a blink of an eye in cosmic terms. Then, something amazing happened. The universe expanded and cooled down enough for protons and electrons to combine and form the first neutral atoms, mostly hydrogen. Suddenly, the fog cleared. The photons were set free from their constant game of cosmic pinball. They could now travel in straight lines across the universe, unimpeded. Now let's rewind the clock for the neutrinos. The cosmic neutrino background tells a similar story, but from a much, much earlier time. We're going to a time before all of that, to the first second after the Big Bang. At this point, the entire observable universe was crammed into a space smaller than a grapefruit. At just 1 second after the Big Bang, the universe had expanded and cooled enough that neutrinos stopped interacting with other matter. They were set free to stream across the cosmos. To truly grasp the cosmic neutrino background, we must first get to know its star player, the neutrino. What exactly is this particle? Imagine a ghost. It can pass through walls, floors, and even people without leaving a trace. The neutrino is the closest thing our universe has to a real ghost. It is a fundamental particle, one of the basic building blocks of matter, just like electrons and quarks. However, unlike those more familiar particles, the neutrino is incredibly shy. It has a minuscule amount of mass, so tiny that for decades we thought it had none at all. It also has no electric charge, which is key to its ghostly nature. This lack of charge means the neutrino ignores the electromagnetic force, the very force that governs light, and prevents you from falling through your chair. Most particles interact with the world through this force, constantly bumping into each other. But not the neutrino. It sails on by, unaffected by the electromagnetic hustle and bustle of the universe. The idea of the neutrino was first dreamed up not from an observation, but to solve a puzzle. In the 1930s, physicists studying radioactive decay noticed something was amiss. When an atom's nucleus decayed, the energy after the event was less than the energy before. This violated one of the most sacred laws of physics, the conservation of energy. Rather than abandon this law, the brilliant physicist Wolfgang Pauli proposed a radical idea. He suggested there was a tiny neutral particle carrying away the missing energy, a particle so stealthy that it had escaped detection. Now that we know what a neutrino is, let's travel back in time, way back. We need to go to the very first moments of the universe's existence. Forget stars, galaxies, or even atoms. We're going to a time before all of that, to the first second after the Big Bang. At this point, the entire observable universe was crammed into a space smaller than a grapefruit. The temperature and density were unimaginably high, creating a seething, chaotic soup of fundamental particles and energy. In this primordial furnace, everything was interacting with everything else in a frantic cosmic dance. It was, honestly, the ultimate particle accelerator. In this extreme environment, particles were constantly being created and destroyed. Pairs of particles and their antimatter counterparts would pop into existence from pure energy, only to collide and annihilate each other moments later, releasing their energy back into the soup. This was happening with electrons and positrons, quarks and antiquarks, and yes, neutrinos and antineutrinos. Neutrinos were being forged in the heart of this cosmic fire, participating in reactions governed by the weak nuclear force. They were just as much a part of the mix as photons, the particles of light. But this state of affairs could not last forever. The universe was expanding and cooling at a phenomenal rate. As the temperature dropped, the energy of the particles also decreased. Then, at a critical moment, just 1 second after the Big Bang, the universe cooled to about 10 billion degrees. At this point, the density and energy dropped below the threshold needed for neutrinos to reliably interact with anything else. It was as if a switch was flipped, and the neutrinos were suddenly set free. While photons were still trapped in a thick, opaque fog for another 380,000 years, the neutrinos began their epic, uninterrupted journey across the cosmos. When the neutrinos decoupled from the primordial soup, they were suddenly free to travel. They began streaming outwards in all directions, a vast, expanding shell of ghost particles, and they've been traveling ever since. For the last 13.8 billion years, this sea of ancient neutrinos has been journeying through the expanding universe. It's a silent, invisible presence that fills every cubic centimeter of space. This vast, cosmic-scale flood of ancient particles is what we call the cosmic neutrino background, or CNB for short. It's a relic of one of the universe's very first moments, an echo of its fiery birth. Think about what this means. Right now, as you listen to this, billions of neutrinos from the Big Bang are passing through you every single second. They stream through the Earth, the Sun, and the deepest voids of space as if nothing were there. Unlike the neutrinos produced by our Sun or distant supernovae, which have high energies, these relic neutrinos are incredibly cold. The relentless expansion of the universe has stretched their wavelengths and sapped their energy. They're now moving very slowly, with an average temperature of just 1.95 Kelvin, which is less than 2 degrees above absolute zero. They're the coldest known natural component of the universe. The existence of this background is not just a wild guess, it's a firm prediction of the Big Bang model. The same physics that so accurately predicts the existence and temperature of the cosmic microwave background also tells us that the CNB must exist. According to these calculations, there should be about 340 of these ancient neutrinos in every single cubic centimeter of the universe, making them the second most abundant particle in the cosmos, right after the photons of the CMB. So, we live our lives immersed in this invisible sea of ghosts from the dawn of time. They're everywhere, a fundamental component of our cosmic reality. Yet we can't see them, feel them, or detect them with our current technology. So we have these two incredible messages from the past. 1. The cosmic microwave background we have received loud and clear. We have mapped it with incredible precision using satellites like Planck and WMAP. It has told us so much about the universe, its age, its composition, and the tiny seeds of structure that would later grow into galaxies and stars. It is one of the strongest pillars of the Big Bang theory. But the other message, the older one from our 1-second-old ancestor, remains unread. The cosmic neutrino background is still a mystery. We are like cosmic detectives who know a crucial clue exists, but we can't find it. We know the message was sent. Our theories of the Big Bang and particle physics are so robust that they demand its existence. The problem is that this message is written in invisible ink. Neutrinos, especially these ancient ones, are incredibly difficult to catch. They have been traveling for over 13.8 billion years. As the universe expanded, they lost almost all of their energy. They are now incredibly cold and slow-moving. Modern neutrino detectors are built to find high-energy neutrinos from the Sun or from violent events like supernovae. But these low-energy relics from the Big Bang are far below the detection threshold of any experiment we have ever built. Catching one would be like trying to catch a specific grain of sand in a hurricane. This sets up one of the most exciting challenges in modern cosmology. How do we read a message that is almost impossible to see? Scientists are not giving up. They are designing new, clever experiments and looking for subtle, indirect clues. Finding this background would not just be a confirmation of our theories. It would open a brand new window onto the universe, allowing us to see deeper into the past than ever before. Even though we can't see this sea of ancient neutrinos directly, they're not entirely without influence. While a single neutrino has an almost impossibly tiny mass, there are, honestly, an enormous number of them, with around 340 of these particles whizzing through every cubic centimeter of space. Their collective gravity, though minuscule, adds up. Over cosmic history, this subtle gravitational pull has played a quiet but crucial role in shaping the large-scale structure of the universe. They're a part of the invisible architecture that has guided the formation of galaxies and the vast cosmic web that connects them. They're a key ingredient in the cosmic recipe. Cosmologists believe that these neutrinos have influenced how matter clumped together in the early universe. Because they were moving so fast in the beginning, they tended to smooth out small-scale density fluctuations. Think of trying to build a sandcastle with very fine, fast-moving sand. It's hard to make small, detailed structures because the grains just won't stay put. Similarly, these hot relic neutrinos resisted clumping on small scales, which subtly suppressed the formation of smaller galaxies. This effect, though tiny, should be observable in the way galaxies are distributed across the sky today, providing an indirect way to see the neutrinos' influence. Furthermore, the total number of neutrinos and their combined mass affects the expansion rate of the universe itself. According to Einstein's theory of general relativity, the rate at which the universe expands is determined by its total energy and matter content. Neutrinos, as a component of that content, contribute to the overall cosmic budget. By precisely measuring the expansion history of the universe and the structure of the cosmic microwave background, scientists can place limits on the total mass of all the neutrino species. These indirect measurements are our strongest evidence that the cosmic neutrino background is real and has the properties our theories predict. This is honestly a beautiful example of how science works. If our current methods won't work, how could we possibly hope to catch one of these ancient ghosts? Scientists are working on a new, almost science fiction-like idea called neutrino capture on a radioactive nucleus. The idea revolves around an effect called inverse beta decay. The perfect target for this is a specific type of hydrogen atom called tritium. Tritium is a radioactive isotope with a nucleus containing 1 proton and 2 neutrons. The key insight is this. What if a relic neutrino from the Big Bang came along and hit one of the tritium nuclei? If it did, it could trigger this exact same decay process, giving the released electron a tiny extra kick of energy. Scientists would need a large amount of tritium, maybe around 100 grams, and they would need to watch the electrons that are naturally emitted as the tritium decays. They would have to measure the energy of every single electron with unprecedented precision. Most of the electrons would have an energy that falls within a specific, well-known range. But if the cosmic neutrino background exists, the theory predicts that a few electrons per year should appear with a tiny sliver of extra energy. This tiny excess energy would be the smoking gun, the fingerprint of a captured cosmic neutrino. It would be the proof we are looking for. This experiment, currently being developed under the name Ptolemy, is honestly breathtaking in its ambition. The technical challenges are immense. The amount of extra energy the electron gets is minuscule, requiring detectors of almost unimaginable sensitivity and accuracy. The tritium itself is radioactive, creating a huge background of its own decays that must be perfectly understood and accounted for. Any other source of background radiation must be eliminated. It is a quest to find a handful of very specific events buried among trillions of others. A search for a whisper in a thunderstorm. The story of how we know the cosmic neutrino background exists is, at its heart, a story about the predictive power of scientific theory. It is a testament to how deeply we have come to understand the laws of physics that govern our universe. The existence of the CMB was not first hinted at by an observation. It was a necessary consequence of 2 of our most successful theories, the Standard Model of particle physics and the Big Bang model of cosmology. The theory doesn't just say the CMB exists, it makes a suite of incredibly precise, falsifiable predictions about its properties. It predicts its temperature today, its density, the number of neutrino species, and its effects on cosmic structure. It lays out a series of clear quantitative benchmarks that we can go out and test with our telescopes and experiments. And in every single test we have been able to perform so far, the theory has passed with flying colors. The indirect evidence we have gathered from these diverse cosmological observations all points to the same conclusion. The cosmic neutrino background is real, and it has the exact properties that our theories predicted. This is one of the most remarkable triumphs in the history of science. It gives us enormous confidence that we are on the right track in our understanding of the cosmos. It transforms the CNB from a mere theoretical curiosity into a tangible, albeit invisible, component of our universe, waiting for the day we finally build a trap clever enough to catch it. In a way, we have already detected the cosmic neutrino background, not by catching one, but by observing the shadow it casts on the rest of the cosmos. However, these indirect clues, as powerful as they are, can never replace the thrill and the certainty of a direct detection. That remains the ultimate prize, the quest that drives physicists to build ever more sensitive and audacious experiments, to finally catch a ghost and read the last unopened letter from the dawn of creation. Why does this matter? Why pour immense resources and intellectual effort into chasing these cosmic ghosts from a past so remote it defies imagination? The answer is simple. It is fundamental to our nature to ask where we came from. This is not just about confirming a theory or measuring a particle. It is about completing the story of the universe, and by extension, our own story. The cosmic neutrino background holds the key to the missing first chapter. It promises answers to some of the most profound questions we can ask. What were the physical laws governing the very first moments of existence? Why is the universe filled with matter and not just empty energy? What is the true nature of the neutrinos themselves? Exploring these ancient signals is what drives science and technology forward. The seemingly impossible challenge of detecting the CNB forces us to invent new technologies and push the limits of precision measurement to frontiers we never thought possible. The techniques developed for an experiment like Ptolemy could have unforeseen applications in other fields, from medicine to material science. The great quests of fundamental science have always been a powerful engine of innovation. The pursuit of knowledge for its own sake, the desire to see what has never been seen before, consistently pays off in ways we can never predict. It is an investment in our future, fueled by our curiosity about the past. Furthermore, understanding the very oldest things in the universe gives us a profound sense of perspective. It connects us to a cosmic history that stretches back 13.8 billion years. It reminds us that we are part of a grand, evolving story. Studying the CNB is an act of cosmic archaeology, digging through the layers of time to uncover the foundations upon which everything else is built. It enriches our culture and our understanding of our place in the cosmos. Ultimately, the search for the oldest light is a search for ourselves. We look back to the beginning because we are creatures who seek meaning and understanding. The faint, ghostly whisper of the cosmic neutrino background is a siren call from the dawn of time, promising a deeper, more complete knowledge of the universe we are so lucky to inhabit. The ongoing exploration, the tireless ingenuity of scientists around the world, is a testament to the enduring power of human curiosity. It is the continuation of an ancient quest, as old as humanity itself, to look up at the sky and wonder, to ask the biggest questions, and to never stop searching for the answers. The cosmic neutrino background awaits, carrying its ancient message from the first second of time, ready to reveal its secrets to those bold enough to listen for its whisper.